This is lesson 410 on the change of base formula. So we've been talking about logarithms. We noticed that logarithms have two parts to it. There's the base of the logarithm and then the value that we're actually taking the logarithm of. So sometimes we're going to run into logarithms where things don't match up too well. If the base and the number that we're taking the logarithm of, if that number is a power of the base, then it's easy to evaluate. However, that is not always going to happen, unfortunately. So sometimes it's beneficial to us to change the base that we're considering. So if we are given a logarithm of the form, so log base a of m, so a is the base of the log, m is what we're taking the logarithm of. If we can't solve that, or if for whatever reason we just don't like working with base a logarithms, pick any base that you do want to deal with. So any b whatsoever, as long as it makes sense. So we're going to only consider positive numbers, and we're not going to consider a base of 1, because that doesn't work. But any other number whatsoever, then we can rewrite any given logarithm in terms of logarithms of that base. So pick your favorite b, then the original log that we started with, log base a of m, is the same as log base b of m divided by log base b of a. So two important things to note here. First off, notice that in this quotient of logarithms, so when we're dividing those two logarithms, we are using the same base both times. Do not use two different bases for these logs. They must be the same base. So if you use base 5 up top, you better use base 5 down below. If you use base 1,000,000 up top, you better use base 1,000,000 down below. So remember to use the same base. Secondly, notice that in our original logarithm, the way we write it, the a is below the m. So log base a, so we kind of write the a down a little bit below our baseline, and the m is on it. So that is kind of reflected in the equation, in the formula that we use here. The a is below the m. So if you forget which one goes up top, which one goes down below, you can use that to help you remember. So the a goes below the m, just in the same way that in log base a of m, we write the a below the m. Now, as far as which base to use when you use this formula, that's actually entirely up to you. There are some circumstances where using base 2 is useful, using base 8 is useful. It really depends on the situation. Frequently, we're going to choose to use base 10 or base e. Remember that for most calculators, not all calculators, more calculators are able to handle logarithms of any base these days. But if you have one of those old-fashioned scientific calculators, this is really your only option. Most calculators can handle only common logs and natural logs. So for that reason, if we're given a complicated logarithm for which we would like to have a good estimate from our calculator, chances are we're going to have to first rewrite it using the change of base formula. So rewrite the logarithm in terms of common logs, log base 10, or natural log, log base e. So we're going to look at a couple examples of where we use the change of base formula to evaluate some more complicated logarithms, and then we're also going to see a more complicated logarithmic equation where we can use this, or there's actually a little bit different way we can handle it. Actually, I take that back. It's not a logarithmic equation, it's an exponential equation, but we are at a point where we could use this change of base formula if need be. So two quick examples, and then we'll look at a slightly longer application problem. So let's consider this one. So evaluate log base 64 of 1 over 256. So this is asking us 64 to what power is 1 over 256? I don't know. That's a good question. So this does not seem to be a logarithm that we can evaluate just as written, in our head at least. Our calculator could handle it pretty easily, but if we need to do this on our own, we're going to have to do something else to it. So 64 and 256, I'm not aware of 256 being an exact power of 64, but I do recognize that 64 and 256, those are both powers of 4. So what I'm going to do is I'm going to rewrite this. I'm going to use my change of base formula to rewrite this in terms of logs in base 4. So I'm going to have log base 4 of 1 over 256. Remember, the number here goes up top, over log base 4 of 64. So see here, the base of the original logarithm is down below, and the original number that we were taking the logarithm of is up top. All right, now each of these still have to think about it a little bit, but not nearly as bad. So let's start with the bottom. So let's see here. So 4 times 4 I know is 16. 16 times 4, that's going to be 64. So this is 64. If I multiply that again by 4, 64 times 4 is going to be 256. So 4 to the third power is 64. 4 to the fourth power is 256. So log base 4 of 64, that's going to be 3. Log base 4 of 1 over 256, well, I know 4 to the fourth power is 256, so 1 over 256 will have to be negative 4. And this is my answer. So log base 64 of 1 over 256 is negative 4/3. Now you could sit and think about this for a little bit. All right, let me take the cube root of this and then raise that to the negative 4th power. And yeah, it's the same thing, but we're gonna run the risk of having an aneurysm or something, or head exploding by sitting and staring at this problem so closely. If we instead use our change of base formula. So I would strongly encourage you, if you run into a logarithm where it's not clear, oh, it's this, try to use your change of base formula to rewrite it in terms of a base for which we can find logarithms just a little bit more easily. All right, we got another one here. Evaluate log base 1/9 of 1 over 27. Now don't freak out that we have a fractional base for our logarithm. Remember, that's perfectly fine. Any positive number other than 1 makes a perfectly good base for a logarithm. So this is okay, but this is definitely not something that we can evaluate simply just by looking at it. So what we need to do is to rewrite this using a base that we know 1/9 and 1 over 27 we can get by taking a power of that base. So 9 and 27, I'm thinking 3's here. So let's use our change of base formula using logs in base 3. So log base 3 of 1 over 27 divided by log base 3 of 1 over 9. All right, so just in case we're not too sure, remember 3 times 3, that's 9, times another 3, that's 27. So 9 is 3 squared, 27 is 3 cubed. So log base 3 of 1 over 27, 3 cubed, that looks terrible. 3 cubed is 27, so 3 to the negative 3 will be 1 over 27. Similarly, log base 3 of 1/9, I know 3 squared is 9, so negative 2, 3 to the negative 2 power will give me 1/9. So my final answer then is 3 over 2. So do make sure that you reduce your final answers. That is important. It's not an optional thing. It's good math grammar. If you don't reduce fractions, sure, we know what you mean, but you don't look very well educated, unfortunately. So make sure you reduce your fractions, and everyone will know that you're super smart. So here, rewrite these in base 3 logarithms, solve those individually, and all together that will give us our final answer. So log base 1/9 of 1 over 27 is 3/2. All right, so let's consider this exponential equation. Now we've been working with logarithms for a while. It's been a little while since we've worked with exponential equations. Remember, the standard technique that we should always try when solving an exponential equation is to try to get the base of each exponential function to be the same so that we can then drop the bases. So here our base is 5, here our base is 4. Yeah, that's not going to happen. There's no way that we can write 5 and 4 as some number to a power, the same number to a different power. So there's no hope of that happening here. So we're going to have to take pretty drastic measures in order to solve this. What we're going to do is we're going to take the natural log of both sides. Or common log would work as well, but I encourage you to use one of the two logarithms that our calculators can handle more easily. So natural log or common log. Technically, you could get by. There might be some reason that we'd want to use log base 5 or log base 4 in this case. But in all honesty, log 5, natural log of 5 and natural log of 4 is going to be the easier thing to handle here. Okay, remember the power rule for our logarithms. Our power rule tells us that when we take the log of something raised to a power, the exponent can become the coefficient of the logarithm. So we're going to rewrite these as 2x minus 1 times natural log of 5 equals, similar story over here, 5x minus 6 times natural log of 4. All right, now I'm going to take an uncharacteristic departure from recommended form. What I would recommend doing when precision is key, when you really need to have the best possible answer, the closest answer you possibly can get, is to leave these two guys as natural log of 4 and natural log of 5. Notice our x is now outside of the logarithm, so this is just a nice plain old linear equation at this point. We don't have to do any factoring, no more logarithms, no more exponents. Natural log of 5 is a constant, natural log of 4 is a constant. So we could solve for x leaving these two guys just the way they are. Now that unfortunately tends to lead to a rather hideous calculation at the very end of the problem. So for the sake of ease of understanding, I'm going to depart from what I'd recommend doing outside of this class, which once again is to leave these guys as stated until the very, very end, and go ahead and put in an approximation for both of them. So I'm going to use my calculator to give me an approximation for natural log of 5 and an approximation for natural log of 4. So when I do that, I get 2x minus 1. Natural log of 5 is 1.609. And then on the other side, natural log of 4, that's 1.386. So multiplying these out, I have 3.218x minus 1.609 equals 6.93x minus 8.316. So from this point on, you're basically going to be tied to your calculator. Unless you're extremely handy with decimals, and if so, kudos to you. But if not, you're going to need to be punching a lot of this into your calculator at this point. So take your pick. Either do everything by hand until the very end and then risk your calculator smoking, or go ahead and do this approximation midway. It's not going to give you as good of an answer, but for our purposes, it's going to be just fine. Okay, so this, as we said, is just a linear equation. We've got decimal coefficients here, but that's okay. No big deal. So let's get our x's on the right-hand side and our constants on the left-hand side. So if I add 8.316 to both sides, that's going to leave me with 6.707, and then subtract 3.218x from both sides. That gives us 3.712x. All right, solving for x, divide both sides by 3.712. That gives me 1.807. Now, since we started with an exponential equation, we don't need to check this actually. There's no danger of this being outside of the domain, so that's just our answer. So there we go. Now, if I had thought through these problems just a little bit more, spent just even a half second more, I probably would have chosen to give you this problem instead. This is actually a bit more interesting in all honesty. So notice I've gotten rid of the coefficient, sorry, the exponent on the right-hand side. We just have this constant, just 4 now. The reason this is interesting is because, once again, we have the same problem that we can't write these two numbers as the same number to a different power. So we're a little stuck. We wouldn't know how to handle this. A key concept I want us to return to over and over again when we think back to this unit is for every exponential equation, there's a corresponding logarithmic equation and vice versa. So here I have an exponential equation that I can't handle. So what I need to do is I need to convert it into a logarithmic equation. So the base of my exponent is going to become the base of my logarithm. So log base 5 of 4 equals 2x minus 1. So this exponential equation here is saying the exact same thing as this logarithmic equation here. Okay, again, this is just a nice, simple linear equation. I do have a logarithm here I have to take into account, but other than that, I just solve for x. So let's add 1 to both sides. So my left-hand side becomes this. Divide by 2. So I get 1/2 times 1 plus log base 5 of 4. That's my x. Now, if I want an exact answer, then I would leave my answer right here. But most likely I'm wanting an approximation, a decimal approximation. So I need to calculate what log base 5 of 4 is going to be. Well, as we've previously noted, there is no log base 5 button on our calculator. Well, probably. So what we need to do is we need to use our change of base formula to rewrite this as natural log of 4 over natural log of 5. This our calculator can handle. So if we put this in our calculator, natural log of 4 divided by natural log of 5, add 1 to it, divide it by 2, the answer that we get back is 0.931. So x is approximately 0.931. And again, what we mean by approximate here is log base 5 of 4 isn't just this decimal. It goes on for forever and ever and ever and ever and ever. But we don't need this answer out to 100 million decimal places. 3 decimal places is going to be just fine. So we're not going to see problems like this, but I do want you to recognize them. I want you to understand how to approach them. These are interesting. These are good. But we may encounter these on our test. So be familiar with the natural log or common log button on your calculator. Once again, using natural log or common log, it doesn't matter. For this problem, you do have to be consistent, however. So don't do natural log on one side and common log for the other. Pick one and stick with it. So long as you're consistent, you're going to be A-OK.